Hi everyone and welcome. My name is Stephanie and I'm the head of clinical affairs at Terra Plasma Medical. Today I want to walk you through how cold atmospheric plasma actually works. Not just what it does in the wound, but why it does what it does. The actual physics, the biology. And specifically, I want to spend some time on the evidence behind the antimicrobial claims, including biofilm, because that's something that comes up a lot in practice, and I want to make sure you have a clear answer when it does. So let's go into it. Most of us learned in school that matter comes in three states: solid, liquid, and gas. That's it. But there's actually a fourth state, plasma. And here's something that might surprise you. It's the most common form of visible matter in the entire universe. Stars are plasma. Lightning is plasma. The northern stars, plasma. Now, when we talk about cold atmospheric plasma, we mean something very specific. It's a partially ionized gas, and the keyword here is cold. It operates at no more than 40 degrees Celsius. That means we can apply it directly to living tissue without causing thermal damage. That's what separates it from industrial plasma you might know. And this technology gives us two things at the same time. It inactivates bacteria, virus, and fungi, and it stimulates the body's own wound healing processes, both simultaneously, from one application. That's really the core of why this is clinically so interesting. How does it actually get generated? Inside the plasma source, small electrical discharges are triggered. Think of it like a miniature, highly controlled thunderstorm happening inside the device's grid. These discharges inject energy into the air right inside the spacer. That energy is enough to start ionizing the air molecules. Electrons get excited, some get knocked out loose from their atoms. And that moment, that ionization is where the plasma state is created. Please let me stay with ionization for a moment, because this is really the key to everything else. If you remember the Bohr atomic model from school, or even if not, you know electrons orbit the nucleus at defined energy levels. When we add energy through those electrical discharges, the outermost electrons, the valence electrons, get knocked loose. The atom becomes unstable. It wants its electron back. And this instability is exactly what generates the reactive chemistry we're working with in wound care. Now the air around us already contains nitrogen, oxygen, argon, hydrogen, carbon, and so on. When these nucleus get ionized, they produce what we call the plasma cocktail, a complex mixture of reactive oxygen and nitrogen species that interact with biological tissue in ways we can measure and document. Now look at the device itself. Plasma Care uses a patented micro-discharge technology. Free electrons are discharged within the plasma source, and they immediately react with the ambient air in the spacer. That's the gap between the device and the patient's skin. The plasma cocktail is generated right there at the point of application in real time. There's nothing being stored, nothing being transported. It's produced in situ, the moment the device is activated and positioned over the wound. This matters for a couple of reasons. It's part of why the technology has a strong safety profile. And it is also why correct technique matters. Consistent treatment distance is important for reproducibility. This brings us to what I think of as the clinical headline, the two-fold effect. Cold atmospheric plasma does two fundamentally different things at the same time. First, the antimicrobial effect. Bacteria, virus, fungi, inactivated through purely physical mechanism. No antibiotics involved, No risk of resistance developed. The second is the activation of wound healing. Cell growth and migration is stimulated. Angiogenesis is promoted. Microcirculation improves. That means better nutrition and oxygen delivery to the tissue, better removal of waste products and toxins, and a reduction in inflammatory responses. And again, there are not two separate modes of two separate applications. This happens in one treatment. The dual action is the clinical value proposition. Now let me go one level deeper into the biology, because I think this is really elegant. On one side, we have the prokaryotic cells, bacteria. The reactive oxygen and nitrogen species from the plasma cocktail form micropores and plasma channels in the bacterial cell membrane. That's a physical disruption. It destroys the internal structures of the cell. The organism cannot adapt to this. There's no genetic mutation that can protect the cell membrane against physical perforation at this scale. That's why across all the research we see no resistance developed. On the other side, we have eukaryotic cells, our own skin cells. And here, the exact same reactive species trigger a completely different response. The cell detects oxidative stress and activates its own repair and regeneration machinery. That leads to cytokine production, release of antibacterial peptides, and stimulation of cell renewal. Same stimulus kills the bacterium and tells the human cell to regenerate. That differential response is not random. It comes directly from the fundamental architecture difference between prokaryotic and eukaryotic cells. And I think when you understand that mechanism, the clinical result starts to make a lot of more sense. This slide shows you that cellular cascade visually. The stimulation of skin cells activity after cold plasma exposure. You can see the chain of regenerative responses the plasma cocktail triggers in eukaryotic tissue. This is the biological basis for the clinical improvement in wound healing, scar remodeling, and overall skin condition that we document in our studies. And here to finish, the complementary picture. The direct action on bacterial cells. The physical disruption of the membrane is rapid, it's comprehensive, and it's non-selective in terms of species. Gram-positive, gram-negative, fungi and virus. The mechanism doesn't care what type of organism it's dealing with. So, to explain the antimicrobial effect a little bit deeper, let's look at the numbers. So, first of all, we have common bacteria, 99.999% inactivation within 1 minute. That's a 5-log reduction. MRSA, the multi-resistant strain that causes so many problems in clinical settings. 99.999% inactivation within 1 minute. So we talk about 6-log reduction. Biofilm, tested on E. faecalis, 99.995% inactivation, again, within 1 minute. Candida albicans, so we move over to a fungi, 99.997% within 1 minute. And adenovirus, 99.999% within 4 minutes. These are in vitro figures. And that shows the antimicrobial effect of cold plasma under controlled conditions. They are underpinning the antimicrobial claims we make clinically. Which brings me to the section I really want you to pay attention to. So let's open the box of Pandora, the biofilm. It comes up constantly in clinical conversations, and I want to address it directly and clearly. The question often sounds like this. You have in vitro data for biofilm, but where is the clinical proof from actual patients? And I want to explain why that question, while completely reasonable, is based on a misunderstanding how biofilm can actually be measured. Here's the reality. Biofilm is a three-dimensional matrix structure. It's not a single biomarker you can detect with a blood test or a swab. To confirm biofilm directly, you need to see it through microscopy or through histology. That means either controlled laboratory conditions or a tissue biopsy from the wound. And the tissue biopsy from an open wound in a clinical trial, that's invasive. It offers zero therapeutic benefit to the patient, and no ethics committee will approve routine tissue sampling just to confirm biofilm presence in a study. And that's for good reasons. So following that to the end, in vitro testing is not the second best option for biofilm evidence. It's the only direct evidence that can exist for any product under any study design. What you see on this slide is our in vitro evidence base. More than 100 clinical wound isolated tested and 99% reduction within 6 hours. No resistance developed, and that includes also MRSA and other multidrug-resistant germs like Pseudomonas. Those are strong numbers, but honestly, that's not even the main point here. The main point is that it's the right methodology. It's the only methodology. Anyone asking you for more than this doesn't understand how biofilm can be measured. And here's the second part of that argument, which I think is just as important. It's not a limitation specific to plasma care. Every antimicrobial wound product on the market faces exactly the same measurement gap for biofilm. Look at what's on this slide. Silver dressings, iodine-based products, PHMB antimicrobial dressings. Every single one of them relies on in vitro microscopy or culture testing for their biofilm claims. None of them have biofilm evidence generated directly from a patient's wound, because, as we just went through, that data point cannot exist. What the entire community uses instead in clinical practice, and what regulators and payers accept as the relevant endpoints, are surrogate markers. Wound swab culture measuring coronary forming units, wound area reduction over time, and clinical signs of infection and inflammation. So when you're in front of a clinician and they push back on biofilm evidence, the answer is straightforward. Our evidence package follows exactly the same methodology as every other product in this space. We're not the exception. We're following the standard. To close that loop, let me show you how this connects to actual clinical study design. Based on the literature, around 80% of chronic wounds are associated with biofilm. That's the clinical reality we're working in. And given the body of research showing significant wound area reduction and documented bacterial reduction in biofilm in vitro, wound area reduction is accepted as a scientifically and clinically established surrogate parameter. It's not a workaround. That's how the evidence framework is built across wound care as a category. Now I want to show you one particularly compelling piece of real-world evidence. Ritchie and colleagues use fluorescence imaging, specifically the molecular technology, to directly visualize bacterial load in 20 patients with chronic wounds. Green fluorescence signals Pseudomonas. Red and orange indicates porphyrin-producing bacteria, so all the other bacteria. After just 2 cold atmospheric plasma treatments, the images show a significant visible reduction in bacterial load across the wound bed. This is as close as current clinical methods get to direct evidence of antimicrobial action in a live patient. And I think these images are speaking for themselves. Ladies and gentlemen, time is running, so let me close with a clear summary of where the evidence stands, because I want you to leave today with really confidence when these questions come up. Plasma care is effective against biofilm. That is proven directly by numerous in vitro studies, including our clinical evaluation report and including results against multi-resistant strains. In the clinical setting, proof is quantitative and indirect. Through wound swab data showing CFU reduction, for example, 73.5% versus 50% in controlled comparisons, and through wound area reduction as a validated healing endpoint. It's not a gap in the evidence. It's the standard of evidence for the entire wound care family. The same logic applies to silver dressing, iodine products, PHMB dressings, every advanced antimicrobial therapy in this space. Our evidence is solid. It's consistent and it's clearly clinical meaningful. Thank you for listening.